Hello everyone, myself Sharda Mase, VIT Pune. Today we'll discuss mass spring system, its modeling and solution, which is application of second order ODE. So let's start with mass spring system, modeling of that. First of all, we'll discuss how physical conditions are described for this mass spring system. Consider the spring which is attached to or whose one end is attached to a rigid support. For example, say that one of the end is attached to ceiling or beam and its lower end is set to free. To the lower end now will load some weight. After loading that spring with some weight, what happens? It gets displaced by its length gets changed by some amount. Say original length is L and now extended length is L plus E. When that mass is attached to the spring, that mass goes in downward direction because of gravity. After a certain time, that spring comes to the equilibrium position. In equilibrium position, say extended length is E. Once it comes to the equilibrium position, we'll give again vibration to the spring in vertical and downward direction. So it starts moving up and down. In this entire procedure, one law that we are going to consider is Hooke's law, which states that force is directionally proportional to the displacement. That is, we call it as restoring force, which is equal to minus kx, where k is constant known as spring constant and x is the extended length. Here negative sign shows that force opposes the motion and acts in upward direction. Dimension of that spring constant k is given by lambda by L, which is restoring force per unit length, where L is the natural length of the spring. Now what happens in equilibrium position? Downward force mg balances the upward force, which is restoring force here, these two forces balances each other. We get that mg is equal to k into E. Here k value is lambda by L. So we can write mg is equal to lambda into E divided by L. Now this weight is set to motion in such a way that it moves in a purely vertical direction up and down. Let x be the position of mass below equilibrium at any time t. Our aim is to find out x as a function of t. So how we are going to form the differential equation using all these given conditions? According to Newton's law, force is equal to mass into acceleration. So in this case, acceleration is d2x by dt square. Mass is m. So m into d2x by dt square is equal to sum of force due to gravity and restoring force. Here force m into g is with positive sign because of force acting in the downward direction, while restoring force lambda times x plus E divided by L is with negative sign because it acts in the upward direction. And the second term we obtain with the help of Hooke's law, where lambda by L is value of k, and x plus e is the total elongation in the length of spring. Using these equations 1 and 2, we can write m into d2x by dt square is equal to minus lambda x divided by L. We can divide throughout by m, which gives us d2x by dt square equal to minus lambda x divided by ml. We'll denote the term lambda by lm by omega square, which also can be written as g divided by e using equation 1. Rearranging equation 3, we get d2x by dt square plus omega square x equal to 0. This is nothing but differential equation, second order differential equation, and this is known as differential equation of simple harmonic motion. Now we already know the procedure how to find out solution of this differential equation. As it is homogeneous linear differential equation, we'll consider its auxiliary equation, which is m square plus omega square equal to 0, whose roots are plus minus omega I. Then required solution of this differential equation is x of t equal to c1 cos omega t plus c2 sin omega t. As you can observe, those cos omega t and sin omega t are two linearly independent solutions of second order ODE, second order LDE, which is homogeneous in nature. If we set those arbitrary constant c1 as a cos phi and c2 as minus a sin phi, we can write x of t as a cos of omega t plus phi, where value of a is nothing but root of c1 square plus c2 square, which can be interpreted as amplitude of oscillations, and the term omega t plus phi is interpreted as phase angle. Thus, this equation is free undamped motion of a mass, which is simple harmonic motion with period t equal to 2 pi upon omega and frequency reciprocal of that period t 1 upon t, which is omega upon 2 pi, can be simplified to 1 upon 2 pi into root of g by e, where we have substituted value of omega using previous equation as root of g by e. So that's it about differential equation. Differential equation of mass spring system, where we have not considered any other force acting on the system. Now what happens if additional to restoring force and force due to gravity, there is some more force acting on the system? This kind of mass spring system is known as undamped motion. This kind of mass spring system and its oscillations are known as damped oscillations or vibrations. So let's consider the motion of spring that is subject to a damping force. In this case, we'll consider that spring moves through a fluid as shown in figure. Real life example of damping force, you can think of shock absorber in a car or bicycle. Now what about this damping force? It is directly proportional to the velocity of the mass and acts in the direction opposite to the motion. This has been confirmed by several physical experiments. So let's denote that damping force by minus C into dx by dt, where C is positive constant called as damping constant and dx by dt represents velocity. So damping force proportional to the velocity. Now, how we are going to form differential equation with this physical information? Again, we'll use Newton's law, which states that force is equal to mass into acceleration, that is m into d2x by dt square, and that is equal to restoring force plus damping force. As you can observe, this damping force is new term here. Substituting the value of restoring force as minus kx and damping force as minus c times dx by dt. Again, negative sign shows here forces are acting in opposite direction or forces are acting in the upward direction. Rewriting this equation, we get m into d2x by dt square plus c times dx by dt plus k into x equal to 0, which is second order linear differential equation, and that too homogeneous differential equation. Now we are interested in finding solution of this differential equation. Again, we'll use similar procedure that we have used earlier. Auxiliary equation mr square plus cr plus k equal to 0. Roots of auxiliary equation minus c plus minus root of c square minus 4mk divided by 2m. Now that root term, discriminant c square minus 4mk, can be positive, can be 0, or it can be negative. Depending on that value, we are going to now consider three cases. First case, when c square minus 4mk is positive. In this case, roots of the equation are real and distinct. Let's say r1 and r2. And as we know, in this case, solution is some constant e to the power r1t plus some constant e to the power r2t. This kind of solution, particular case, is shown in the figure. How the graph of solution look like, where c square minus 4mk is greater than 0. These kind of oscillation are physically termed as overdamped. Now come to the case 2, where c square minus 4mk is equal to 0. In this case, roots are real and equal, say r1 and r2 both taking value minus c divided by 2m. In this case, solution is k1 plus k2 into t e to the power minus c upon 2m into t. Graph of solution in this case resemble to previous situation. This kind of damping called as critical damping. Now last case, where roots are complex, when c square minus 4mk is negative. Roots I'll denote by r1 and r2, which occurs in complex conjugate pair minus c divided by 2m plus minus I times omega, where omega is root 4mk minus c square upon 2m, and required solution is e to the power minus c divided by 2m into t, k1 times cos omega t plus k2 times sin omega t. This case physically is described as underdamping, whose graph of solution is as shown in figure. So that's it about mass spring system described with the help of second order LDE with three kinds of solution in three kinds of cases. Thank you.